Okay, guys, do you have any doubts on the week three's lecture? Sorry. If you have any doubts, please go ahead first, then I will start after that.
Hello, sir. Good evening, sir.
Yes, good evening.
Sir, will you explain reversible oxygen binding and transport process, sir? I didn't understood in that video, so that's why I'm asking.
Okay, I will cover it. So actually,
That is fourth week, third lecture, I think.
fourth week.
Yes, sir. Fourth week, third lecture.
Okay, actually, I'll cover third week today, and then fourth week in the next week. I will definitely discuss about what is the oxygen transport system, that one.
Yes, sir.
That is the iron, porphyrin, myoglobin or hemoglobin.
Sir, hemoglobin,
Okay,
hemoglobin. And types of myoglobins is there now, sir. Deoxymyoglobin and oxymyoglobin. So
okay,
I confused oxidation numbers and spin.
okay. Definitely, I'll recover.
Okay.
Okay, Kalpana. So your question is the oxygen transport system by the hemoglobin and myoglobin.
Yes, sir. Yes, sir. Yes, sir.
So hemoglobin and myoglobin both are containing same similar kind of hem unit, and that is the iron porphyrin system, where the porphyrin ring, which coordinate with four iron center with by four coordinate bond, and the one axial histidine moiety, that is axially bounded to the iron center in deoxy form. So in myoglobin and hemoglobin, both are kind of similar, but my hemoglobin is has the four subunit, and myoglobin has only one subunit. So let us think about the deoxy form. That is the no oxygen is bound with the iron center. So it is. I am drawing the cartoon structure. If you want to draw the actual porphyrin structure, then I will definitely draw that. But you will find everywhere in internet also. Uh,
Okay.
so this is the iron center coordinate with the five four nitrogen containing porphyrin system. Sorry. This is the Fe, nitrogen, 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 and axially bound with axial histidine and histidine. And here the protein chain bound with myoglobin and hemoglobin. Here present the distal histidine. Okay. See
Okay.
this distal histidine playing a crucial role for the
Okay.
reversible binding. So
Okay.
initially deoxy form iron is the iron 2 center. That is the D6 system.
Okay.
D6, and that is the Low spin or high spin?
Sir, deoxyhemoglobin, high spin.
Yes. D6
High
high
spin.
spin.
Okay. Okay.
High spin. So right now, if it is bind with the oxygen, it is not showing that D6 after part. Okay, it 1 minute, just a minute. Someone joining. If it is bind with the oxygen, that is the
Okay.
reversible way. Because of this histidine is playing, distal histidine is playing for the stable iron oxygen bond. It's also making that disturbance for binding the oxygen with the iron, and also it helps to stabilize also oxygen bond. It depends on your environment. If hemoglobin is your lungs, here your in the oxygen, this is actually, this process is the equilibrium process. You know the law from the last atelier principle. So where the your reactant is sufficient, you can shift your equilibrium in a definite direction. Do you know, Kalpana?
Ah, yes, sir.
Yeah. So in your lungs, that is, oxygen concentration is high. But
Hi.
in your cell, the oxygen concentration is low. So what happens
Okay.
in lungs? You providing the oxygen amount sufficient that forward the oxygen binding at the iron center.
Okay.
So it's and in the cell, what happening, the oxygen concentration is low, so it follows the reverse reaction.
Okay.
So that's how the reversible oxygen binding happening in lungs. Lungs, it is also binding with the iron, and in the cell there is an oxygen concentration is lower than the your lungs. So your oxyhemoglobin release the oxygen.
Oxygen. Okay.
So here the in the deoxy form, oxy form, how it looks like is the in the deoxy form, this iron center is lying below the porphyrin ring. This is the porphyrin ring. This porphyrin ring below, it's lying below the porphyrin ring because of the iron two. Iron two has a different kind of size. Okay, it cannot
Okay.
fit to the iron porphyrin rings. So it's lying below the porphyrin system. When it becomes the iron 3, that is the when it binds with the oxygen, it becomes the iron 3. Size is different, it's smaller than the iron 2, and it comes to the at the porphyrin plane. Okay,
Ah, okay, sir.
it's
So
come.
iron plus 2 is oxidized to iron plus 3.
Yes,
Is
yes,
it right?
yes, yes, yes,
Okay.
yes,
So in deoxy form, iron is high spin, and deoxy oxyhemoglobin is low spin.
yes, yes, yes. Oxyhemoglobin is low spin.
Oxyhemoglobin is low spin. Okay.
So here comes the option of the cooperativity system. So your hemoglobin is there, has a four subunit, right? So four subunit means it connect with some way, that is the salt bridge connection. Four subunit connect with a salt bridge interaction. Whenever your oxygen, one oxygen is bound in a iron center, this iron center moves upwards and fit at the plane of the porphyrin ring. As a result, axial histidine, this axial histidine also moves in the oxyform, and the protein chain also moves, and this protein chain moving of this protein chain also breaks the salt bridge interaction, and the hemoglobin comes to tense state to relaxed state. So affinity towards the oxygen binding, that's how increases when your system was in tense state. It cannot binding the oxygen. When one solid is broken, so another iron center is free and becomes in a relaxed state. So it always try to bind to the another oxygen, and and that's how the affinity towards the oxygen binding increases. This is known as the cooperativity. Okay,
Okay, sir. Okay.
fine.
Ah, fine, sir. Good, sir. Okay, sir. Thank you.
Yeah. Any other doubts? Okay, sorry. Any other doubts?
Sir, one more doubt is, sir, just wait, sir. Just now. Sir, please explain catalase and oxidase.
Yeah, yeah. Today I'm going to cover this catalase and oxygenase, all those things.
Oxidase, yes, sir.
Okay. So, uh, who are right now? Nava, Padmaja. Nava, do you have any question?
Sir, no, no questions, but I need a total entire topic. That's why I'm asking, sir.
Okay, okay,
I confused in the topic.
okay.
Catalation process, how to conversion in oxidase and
Yeah, yeah.
catalase.
I'll cover. I'll cover. Catalase and oxygenase both are different enzymes. They have
Yes.
different kind of role. So both have
Yes.
the kind of iron kind of center, iron heme center, but they playing a different role, different reaction.
Mm.
Okay, so
Oh,
I'm starting today's discussion. Uh, just a minute, wait.
okay, sir.
So, so what we are in last class, we just discusses about the how the energy has been utilized for our respiration process, and the energy mainly comes from the oxygen reduction, that oxygen reduction and the glucose oxidation. So where the phosphate, the store energy stored is been in as a ATP, and that ATP breaks one of its phosphate linkage and releases huge amount of energy and becomes the ADP. So whenever it requires energy, the ATP becomes ADP, and when we need to store the energy, that is the ADP becomes ATP, convert to ATP. Now comes to the picture or system like oxygen, reactive oxygen species. So to activate the oxygen in our atmosphere, there is a 21%, near about 21% of oxygen. Our skin also have different kind of organic molecule, inorganic molecule, but it cannot reacting with the oxygen. Why this is not happening in atmospheric oxygen? The If we see the mo diagram, the homo of the oxygen, that is the pi star. Okay, so pi 1 pi 1 g. So oxygen, oxygen. Okay, this 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 are the both the oxygen in a triplet, the oxygen is triplet state. Okay, so triplet state, the oxygen is not active. It cannot react with the any other species. because of triplet can react with the system which are in triplet state. But in our system, that the our uh, hydrocarbon which are present in our skin, those are in singlet state. So we need to convert the oxygen to the singlet state, then it can react with the oxygen. So here play the different kind of enzymes and activation energy requirement. So for that to purpose to do the singlet, to say formation of the singlet oxygen, we can make two different kind of singlet oxygen. One is kind of both the electrons should be in one atomic orbital, a molecular orbital, or otherwise both the electron are in different orbital with a defined spin. So possible way is that possible way both the oxygen in one orbital, or that is the both the in defined orbital with a defined spin, and that is the our initial one, singlet one. Oh, sorry. Okay, this is the singlet, singlet. This is the energy. Okay, so at least we need to uh, provide the energy that much. That is around, this standard value is around 22.5 kilocal per mole, and we have to provide somehow. So for that, here the thermal energy and the enzymes playing the crucial role. So we also covered the how the electron transfer started from the pyridoxine to the, it comes to the cytochrome AA3 to reduce the oxygen. So again I am going through with this. So it is the main purpose of this talking discussing with this, because of the from where our electron is coming, and through what and why this is coming to the earth, the oxygen. So initially, if we reduce some organic molecule, oxidize some organic molecule, it's give you a electron to the your system. So and that electron has been transferred with a subsequently and simultaneously from a pyridoxine to NAD to flavoprotein to cytochrome B, cytochrome C, and then cytochrome AA3. From the cytochrome AA3, this oxygen is reduced to water. So all the process is a simultaneous way. So starting from the organic reaction, organic molecule becomes oxidized. It provides the electron to the pyridoxine. Uh, Pyridoxines. and pyridoxine to comes to NAD. This NAD to lipoprotein. Lipoprotein to cytochrome B. Cytochrome B to cytochrome C. From cytochrome C2 it comes the electron. Cytochrome AA3. From where the oxygen reduction happening to water. So all the process is the energetically favorable. Delta G for this process is negative and becomes the simultaneous. And the here the potential is around minus the electron transfer from standard redox potential of the pyridoxine is minus 0.4 volt versus RH, and this potential is around this potential is my 0.815 volt versus RH. So coming from the higher negative value to lower negative value, the electron transfer happening in a simultaneous way because of the delta G is negative. So and so so the process is uh, simultaneous, and now the question is the who are doing the oxygen reduction. It is known as the cytochrome C oxidase. How it looks like? The cytochrome C oxidase contains two subunits. One is the cytochrome heme A and copper A. Another is the heme B and copper B. So both the both uh, two copper center and two iron center is present in the cytochrome C oxidase enzyme. So the cytochrome C oxidase. Cytochrome C oxidase was the subunit. How subunit looks like: copper, sulfur, sulfur, copper, copper, O, glutamate, glutamic acid. That is the glutamate. Here is the histidine, histidine, and this is the cysteine. This is also cysteine. So cysteine. This is N histidine. This is methane. Oh God, lots of people are joining. Okay, and and also it contains, this is known as the copper A now, and also it has a iron center, iron porphyrin center, Fe N N N. In the porphyrin, I will always be prefer to use the cartoon structure. One is the N histidine, another also N histidine. Okay, so him A. Okay, this is the uh, one part of this cytochrome C oxidase. Another part of the cytochrome C oxidase is, this is the copper and N histidine, N histidine, N histidine. Okay, and it also has the heme unit. This is the copper B subunit. This is the, this is the also iron porphyrin and histidine, and one side of this system is vacated. Here the both the copper, here in the heme A and copper A system, both the copper are saturated, and the in the subunit B, where the copper center also vacated by a coordination site, and iron center also vacated with a coordination site. So here, uh, these guys are very late. Okay, and this subunit A play the electron transfer role. This is the, sorry, color change, to different colors. This is the subunit A, and the subunit B. Okay. Okay, so this is the both the system. This subunit A play the role for the electron carrying only, and as it is not vacated with any coordination site, it cannot bind with the oxygen. Whereas the subunit B, it can binds with the oxygen. Here the one vacant site also here. This is the vacant site, and this is the vacant site. Vacant site, it can bind with the oxygen. So now question is that there is a two possible site. So which site can bound with the oxygen? So here two possible pathway has been provided, but which one is the correct? Nobody can prove right now. But actually, more preferable one is the bind with the oxygen through the iron center. So initially in the okay, okay, initially in the relaxed state. So iron is iron 2, copper is copper 1. So I'm drawing. uh, 20 iron and the copper. Oh, this is the copper, it's scaffold with ligand scaffold. This is the iron with heme unit. drawing carbon structure. Okay, and it's bound with the oxygen, takes the oxygen, follows two different pathway. One is the bound through the iron center, and that is the bound through the copper center. Let's suppose the your oxygen is bound to the uh, from the iron center. So how it looks like from the superoxide dot, okay, dot minus, and iron becomes iron 3, is the iron 2, copper 1. So, and here copper is present, and with the ligand scaffold, the in histidine and iron porphyrin, and it again takes bind with the oxygen. It forms the superoxo peroxo species. That is with the bridging with the two metal center. One is the copper, another is the iron. So copper, how it looks like oxygen, oxygen, iron. Copper becomes copper 2, iron becomes iron 3. So and and the alternative pathway is that, so your iron iron is here, and nitrogen, 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 nitrogen. The copper center actually binds that way. Sorry, the drawing is very bad. Handwriting also very bad. Okay, so super as a superoxo mode, and this iron becomes iron 2. Again, it transfer to one oxygen with bind with the iron center. Again, it forms the peroxo bridge bond. With all the ligand is here. Ligand is here. Okay, this how, but possible more favorable one is that this one. This is the more favorable one. This is the more favorable one. Okay, so then move to the mechanism part. So it takes the oxygen, it forms the copper 2 iron 3 peroxide species. So it already formed. Let's suppose, yes, let's suppose the starting from the initial one. So your copper, uh, let it be copper 1 and iron 2. Don't think about the ligand pair. There is ligand pair. Only the subunit 2 is responsible for the reaction, and the subunit A is responsible for the electron transfer. So starting from the subunit B in the dense state, relaxed state, relaxed state. That means the copper 1 and the iron 2 center. It takes the oxygen. It forms the copper, generally prefer 1. I'm drawing the prefer 1. There is the copper 1 and iron 3 superoxo species. Iron 3 superoxo species dot minus. And this is the iron 3. And this iron 3 superoxo species again reorganized with themselves and transfer one electron to the superoxide. It forms a peroxide from the copper center, copper 1 center. The copper 1 center becomes a copper 2. Copper 2, oxygen, oxygen, iron 1, 2, 3, iron 3. This copper 3 oxo species takes two electron, one electron, and two proton, forms the all the process is reversible. Forms two proton and uh, H plus electron, one electron, forms the copper 2. Also, the coming very late. Copper 2 and OH2, and it forms the iron superoxide species. Iron 4 superoxide species. This iron 4 superoxide species takes one electron, from the copper 2 OH2, and the iron 3 OH. Sorry, this is the OH, not the OH2. So again, uh, sorry guys. Okay, and this also takes two proton and releases two molecule of water, generates copper 2, copper 2 and iron 3 species. This is also taken another two electron to forms copper 1, regenerates the copper 1 and the iron 2. So how many electrons involved over here? Here one electron, here is the, sorry, here there will be one electron, electron 2, and here is the two electron. So total four electrons process, four electron, and how many protons? Here is the two protons, here will be the two protons. So four proton, four proton process. So the total reaction, whole reaction involve the four electron and the four proton. Okay. So till now, do you have any question?
No, sir.
Oh, okay, fine. So coming to the next part. So cytochrome C oxidase, it forms the oxygen to, it transfer the oxygen to water with a different forming of different superoxide species, peroxide species, and the hydroxide species. But whole reaction process is the formation is the your oxygen 2 plus 4 electron plus 4 proton to 2 molecule of water. Okay, so this energy requirement is around, I think the thermodynamic potential is around E0 value equals to plus 0.815 volt. Okay, so here the whole process happening, but this 4 electron, this potential is required only for thermodynamic potential. That means your 4 electron and the 4 proton should be provided in a simultaneously way, in an instant manner. That means in your certain time, your all the 4 electron and 4 proton will be transferred to your system. But this is only happening in case of thermodynamic, as well as the some kind of enzymes that can do that. Here the cytochrome C oxidase also doing same thing. Now question is that if the electron transfer is not for by the 4 electron, it by 1 electron or 2 electron or 3 electron, so what will happen that times? So that times, so let's suppose electron transfer, one electron transfer happening. So here is my oxygen O2. It takes one electron. It generates the O2 dot minus. That is known as superoxide. Superoxide. Okay. This superoxide again, if take one electron and two proton, it forms the hydrogen peroxide. It's 2O2. This hydrogen peroxide, if take one electron and one proton, it generates the very poisonous hydroxyl radical. Water, sorry, water plus OH dot OH dot radical, hydroxyl radical. That is the hydroxyl radical. Okay, and from here to another electron transfer to form two molecular atom. So in the imine process, my very poisonous hydrogen peroxide, superoxide, and the hydroxyl radical forming. Uh, is the hydroxyl radical, hydrogen peroxide, and superoxide also forming. So those are very poisonous to our health. So we always know, always aware about that we need some antioxidant uh, in our body. So different kind of antioxidant can reduce this superoxide and hydrogen peroxide or hydroxyl radical to water molecule, and that can remove from our body. So different some of antioxidants are, we know, in our organic that is the organic compounds, uh, from the lemon kiwi, tea, that has lots of antioxidant. So during our formation of this superoxide and hydrogen peroxide, we need to take some fruits like kiwi, orange, tomato, black tea, orange, onion, pomegranate. Also, it has lots of antioxidant. So that's why the doctor mainly prescribe the lots of antioxidant, like different kind of fruits. And so here biology also doing a another uh, interesting chemistry in our body. So that is known as the interesting chemistry, that is the way to reduce this superoxide, hydrogen peroxide and hydroxyl radical. So different kind of enzyme has been also in it has been used. One of them is the superoxide dismutase. This enzyme is superoxide dismutase. Dismutase. Okay, this superoxide dismutase, what the role of this superoxide dismutase? It reduces, it disproportionate the superoxide which form in our body to water and the oxygen molecule. Dot minus plus 2H plus 2 H2, sorry, not water, there is a hydrogen peroxide and the oxygen. So for that transformation, so different kind of enzymes also has been found in our nature. That is, one is the zinc copper superoxide dismutase. Zinc copper SOD. Uh, Another is the manganese SOD. Manganese SOD. Iron SOD. People has been well studied the onto the, sorry, this is the jargon. JD, no, that JD. So people already has been well characterized the superoxide zinc copper superoxide dismutase. So its active structure is like your this copper center, copper bound with three histidine moiety, and histidine, then histidine, then histidine, and one histidine moiety bridge with the two metal center. Here the zinc is present on in histidine, aspartate, and the histidine. O aspartate and the in histidine. And the copper is copper 1. So hold the reaction process is two kind of reaction happening over here. One is the superoxide. This is the superoxide dot minus to form oxygen plus electron. Here the potential for this reaction is around uh, wait for 1 minute, around plus 0.33 volt versus NH. And the second reaction is the this superoxide takes an electron to form the, sorry, sorry, sorry guys, just wait for 1 minute because of it has a limit of 1 hour. We have to close the meeting and again restart the our meeting. Just 5 minutes, give me 5 minutes, again come back. Okay. Is my screen visible to all? Oh, is my screen visible to all?
Yes, sir.
Uh, did you find the pad one? That is the whiteboard and the writing one. Did you get that? Okay. So where I was, the value of or the second reaction is that takes one electron to O2 2 minus. That E0 value is around is plus 0.89 volt versus NHE. So overall reaction is 2O2 dot minus 2 oxygen plus O2 2 minus. So delta G0 for this reaction. So we can easily calculate from the E0 value. Uh, from the E0 value, that is the delta G0 equals to minus NF E0. E0. So that is value is around minus 117.73 kilocalorie per mole. That means the process is simultaneous. Now the question is how this reaction happen, mechanism part. So two mechanism has been proposed. One is the your metal center playing the electron transfer role. Uh, as we know, this is the reaction of the disproportionation reaction. Your reactant divided into two part. For one part is in a different oxidation state, another part is in different oxidation state. So this is the oxygen superoxide one, this is the oxygen one, and this is the peroxide. Here is the oxidation state is 0, here oxidation state is -1, and here is the each oxygen atom has the oxidation state of -0.5, sharing to one electron sharing by the both oxygen atom. And the coming to the mechanism part for the in the taking first initially thinking taking the your metal center is involved. So how the reaction will proceed, uh, metal in a n plus oxidation state, it binds with the transfer it electron, sorry, electron to the superoxide, one electron, metal becomes the metal n plus 1, and the superoxide, sorry, n minus 1, it take uptake electron from the superoxide or vice versa. That way it can form the -1 plus oxygen, and sorry, this is the mechanism one. And in the formed metal, that is the n-1 oxidation state, it again reacts with the O2 dot minus 2. It gives the electron to the O2 dot minus the low valent metal center. It again regenerates the Mn plus O2 2 minus, and again this one takes two proton to form Mn plus H2O2. Okay, and in the mechanism 2, what they are suggesting is the disproportionation way mechanism. Mechanism 2 is that Mn plus only your oxygen adduct product is formed. Superoxide adduct product formed O2 dot minus to form Mn plus oxygen superoxide adduct product dot minus, and this Mn plus superoxide adduct product again takes one superoxide and transfer their electron to themselves and forms the hydrogen peroxide and the oxygen. This Mn from there also. Okay, so from here to take another superoxide Mn plus O2 2 minus adduct product plus oxygen is coming out from the system, and it takes two H plus to form N plus H2O2. Okay, and this for the copper zinc superoxide dismutase followed the mechanism, mainly followed the mechanism 1, where the copper center is initially the copper 2. It takes one electron from the superoxide. It becomes the copper 1, and the copper 1 again reacts with the superoxide, another superoxide. The copper 1 transfer electron to the superoxide. It becomes the peroxide, and that peroxide takes two proton to generates the hydrogen peroxide. And coming to the iron SOD, how it looks like. So comparing the three superoxide dismutase, one is the copper zinc, uh, as we discussed about the how it looks like, n zinc aspartate n histidine, here is the 3n histidine, n histidine. Okay, link with the one histidine moiety. Here the protein chain, other protein chain is present. In the iron, it looks like, change the color, iron how it looks like. Here is the N histidine. Here is the N histidine. Here is the aspartic acid present over here. O double bond O C here ASP aspartate, and here is the N histidine and one water molecule. Okay, this is the iron. This is the iron superoxide dismutase FeSO-D, and the manganese one. All are similar. Only metal center change to manganese one. It similar looks like iron SOD, and it only change is the metal center. Here is the manganese N histidine. Here is N histidine. Here is the OH2. Here is the aspartame molecule. ASP and the N histidine. So here comparing both the all the SODH reaction rate, all those enzymes has very high rate of conversion of superoxide to hydrogen peroxide and oxygen. So this is the rate for the copper zinc superoxide dismutase is around 2 2 into 10 to the power minus sorry 10 to the power 9, not the minus, 10 to the power 9 mole molar inverse second inverse, and for the iron one is around 3 into 10 to the power 8 molar inverse second inverse, and for the manganese one 5.6 into 10 to the power 7 molar inverse second inverse. So here the your system is taking the superoxide and the found the oxygen as the and the hydrogen peroxide. But why these enzymes are too specific towards the substrate scope? Let's think about the copper oxide dismutase, copper zinc superoxide dismutase. It has a definite enzyme cavity and the pathway where the only the superoxide can come and bind to the copper center. Here the zinc is playing the play role of the stabilization of the your enzyme, and here only active center copper center is playing the uh, activation of the superoxide. And scientists also prove that the only copper center can reacts with the um, superoxide. How they did the experiment? They, they took the enzyme and treat with the EDTA. As we know, EDTA a very strong coordinating agent. It can capture almost all the metal ion. So it capture the remove the copper and the zinc from the superoxide dismutase. So how? So this is the copper. Sorry, copper N A zinc treat with they treated with the EDTA minus, and take all the metal, only present is the histidine, histidine and the other ligand. Left is histidine and other ligand. Histidine plus other amino acid chain. This is a very interesting uh, experiment. We always do this kind of control experiment to prove that only this metal center or only this one is the active for the following reaction, and then they add only zinc Zn2 plus. Okay, so but they found no activity towards the superoxide. The species found not active towards superoxide disproportionation. Now, taken this solution, they treat with the copper 2 plus. They found the both the metal substitute here the zinc and copper are present. Here the both are the copper. Now both are the copper and copper. Both are copper. Now both are the copper. They found it active towards superoxide disproportionation. But drawback is that problem is that this is not stable in thermal condition. It's thermally this protein, the protein here the only the active center. It's surrounded by a huge protein chain. This protein is denatured. That means protein structure is breaking, and this is not the enzyme is not stable at a higher temperature. So it has issue with the thermal stability. Thermal stability. There is no thermal stability. Now they did what they did. They treat with the zinc, one equivalent of zinc, one equivalent of zinc 2 plus. Again they regenerates his system and found the similar activity towards the similar activity towards superoxide disproportionation. Okay, so in question, here zinc also has a play role for the stability of the superoxide dismutase, and nothing else with the zinc. Only the copper center is play the role for the electron transfer and the disproportionation reaction. Now problem is that This superoxide dismutase, what they forming? The it forms it O dot minus 2 oxygen and H2O2. This H2O2 also a very harmful to our body. So we need to remove this harmful hydrogen peroxide. So nature also here develop different kind of enzymes that is known as different enzymes like catalase, peroxidase, chloroperoxidase, lignin peroxidase, and cytochrome C peroxidase. With the neck coming to the catalase enzyme. So the catalase enzyme is basically nothing but a heme unit for the axial ligand in tyrosine. So catalase coming to the catalase. So catalase is iron heme unit, heme unit, nitrogen, nitrogen, nitrogen. Axially ligated with tyrosine. And sixth position is coordinated with the water molecule, weakly bound. This enzyme mainly play the role to transfer hydrogen peroxide to water and the oxygen. Main role is that hydrogen peroxide to water plus oxygen, two molecule. This catalase enzyme is also found nearly all the living organisms where the oxygen is generally reducing. Now coming to the mechanism part, the heme tyrosine bounded the relaxed state in the initial state, that is the iron 3 center. This is the iron 3 center initial state. This iron center is below the below the porphyrin ring, but hemoglobin and myoglobin, this iron is uh, at the iron 3 at the plane of the porphyrin ring, but here catalase in the catalase enzyme, the iron 3 is below the porphyrin plane. Now coming to the mechanism part, Fe, let's think about, this is the at the below the plane of the ring, and this is the tyrosine. So it takes the hydrogen peroxide H2O2 to convert water molecule, and the system becomes iron superoxo, iron 4, iron 4 oxo species, iron 4 oxo species. This is this is this is a very important intermediate, and this is very unstable intermediate also, and the iron becomes at the plane of the porphyrin system, and it forms the iron 4 superoxo. This is the iron 4, and it transfer the two electron. So this ring becomes the positive cation radical, and the axially is the tyrosine moiety. Okay, so and again another molecule of H2O2 to oxidize to oxygen, and the two electrons neutralize the this positive cation radical, and the iron 4 to transfer the iron 4 to iron 3. Plus water, this oxygen becomes the water. And by taking a control experiment, like if we uh, if we label this oxygen by the different isotopic level, where we found that the oxygen, only the oxygen is the labeled oxygen. So that means there is, in this reaction, in the below reaction, there is the iron oxo species to form generation of the iron 3. This transformation, the oxygen bond cleavage is not happening. Okay, so any further question about the catalase enzyme? Okay, if not, then go to the, there is another enzyme which can convert hydrogen peroxide to different product with the help of organic molecule transformation, that is known as the peroxidase enzyme. Peroxidase enzyme. Peroxidase. So the main reaction is that is the reduced organic species. Let's suppose RH plus H2O2 to form a species R plus H2O. I going. Someone wants to join. Okay, and the different kind of uh, peroxidase has been found. One is the cytochrome C peroxidase, glutathione peroxidase, meloperoxidase, ascorbate peroxidase. Now Horser dis peroxidase, sorry. And how the active center looks like. Here also a this is also a heme unit, and axially ligated with the histidine molecule. So this is also a heme unit, Fe, nitrogen, 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 nitrogen. Axially ligated in histidine, and the weakly bound water molecule. Ah, okay, and this let's suppose the think about the ascorbate peroxidase. How it's happening? The ascorbic acid. You know the ascorbic acid. What is the ascorbic acid? This is the ascorbic acid. I'm writing the structure of the ascorbic acid. OH, OH. This is a double bond O. This is above the plane, and it is the below the plane. This is the OH. So this is the ascorbic acid. It transferred to the dehydroxyascorbic acid. That means these two oxygen OH group oxidize to ketone. So this is the H2O2 and ascorbate rate peroxidase in presence of peroxidase. Sorry, here will be a double bond. It forms the oxidized species. So this is double bond O. This is double bond O. This double bond O is above the plane, and OH. This is OH and two molecule of H2. So here this hazardous hydrogen peroxide becomes water, and the pure ascorbic acid becomes the dehydroxy ascorbic acid. That's how the biology has been utilizes the this kind of peroxidase enzyme to reduce the amount of hydrogen peroxide in our body. In the mechanism part, here also it's also going to the same uh, unstable iron 4 oxo species. So how? So taking iron, only thinking the iron is the iron 3, and this is also similar. Below the I'm, I'm only writing the histidine axial ligand. It is below the plane of the porphyrin ring, and it takes transfer to the H2O2 to water, forms the iron superoxide species iron 4, and the ring becomes a positive cation radical plus dot, and that plus dot in presence of ascorbic acid as a sacrificial electron donor. That means your um, that means it's ascorbic acid you acting as a electron donor. It becomes the S dot plus H plus. So it becomes the iron 3 oxo species. It transfers the two electron iron 2 sorry iron 4 oxo species. So again one equivalent of ascorbic acid transfer two electron is H2 transfer two electron is H dot plus to regenerates our OH minus plus OH minus and regenerates the resting initial state, and again it is capable to cycle another another uptake the hydrogen another hydrogen peroxide. Okay, so another important enzyme is the chloroperoxidase. So now coming to the chloroperoxidase. Chloro peroxidase. So chloroperoxidase also has a same iron porphyrin center, only axial ligand is different. Fe, Fe, iron porphyrin system. Here the S16 16 is present and weakly bound water molecule. Okay, what it can do? It can transfer the organic molecule in presence of a halide molecule. Let's suppose RH, your organic molecule, and RH plus X minus plus H plus, and in presence of H2O2, it transferred to AX and to H plus. So sorry, RX. This becomes here, and this hydrogen peroxide comes to sorry 2H2. Oh, it's coming the last moment. Okay, this is the main reaction. Let's think about the one reaction in definite organic reaction. That is the dimidone, dimidol to dimidone transformation to chlorodimidone. Here the dimidol Cl OH chloroperoxidase, short form CPO. One is Cl upwards, another is Cl downwards, and this becomes the double Monroe. Rest of the thing are same. Okay, so this is the reaction. How this reaction happening? Let's suppose think about the mechanism part. So mechanism part means Fe center. I'm not writing the rest of the porphyrin one. Only S. It takes the iron is 3 plus. This takes the H2O2 and remove the water. H2O2 to water, two electron process, two electron reduction happening over here, and the Fe becomes 4, 4 plus 4 plus and the ring becomes dot plus cation radical. So this cation radical, from this cation radical, the halide Cl minus, how it comes? The nucleophilic attack. This nucleophilic attack happening to the oxygen, and the oxygen double bond becomes the single bond oxo species. So this is the system Fe system. Now Fe becomes 3 plus, and the oxo species Cl is become the minus, and the S is remaining over here system. And again this species has also a takes one proton. It becomes the influence of proton. It becomes the OH, and how the reaction happening forward. That this dimidol here, the dimidol, one chlorodimidol Cl OH becomes play. Okay, so proper way. Oxygen, hydrogen. This bond breaks. It come. It goes to the chlorine center. The chlorine center broke. So it forms how it looks like. Your system becomes iron Fe Fe 3 plus. It's become OH and takes one proton from the outside. So OH2. Rest of the thing are remaining. Here the two chlorodimidon is formed. Cl Cl methyl methyl didimidon. Okay, fine. So now this is the peroxidase system. Now coming to the point of the oxygenase enzyme. These oxygenase enzyme are also reduce superoxide to superoxide to the water, and from the with the help of the defined organic molecule. This oxygenase enzyme, two kind of oxygenase enzyme has been found in the nature. The oxygenase enzyme is a dioxygenase enzyme, and there is a monooxygenase enzyme. The dioxygenase enzyme, I'm telling, let about write something. Oxygenase, oxygenase, oxygenases. So dioxygenase, dioxygenase. In the dioxygenase, the one substrate takes influence of uh, superoxide to form substrate product to molecule of substrate, and the monoxide di, di, dio, mono, monooxygenase monooxygenase oxygenase, it only one oxygen is bound with the substrate molecule. substrate plus O2 dot minus in presence of H plus 2 electron forms substrate O2 dot minus 2 H2. Okay, so this is the system. Let's suppose think about that some reaction of the monooxygenase dioxygenase enzyme. Dioxygenase dioxygenase change the color. This is the benzene ring. Benzene ring. The monodioxygenase risky dioxygenase risky the name of the scientist who discovered this enzyme dioxygenase to form it form the this is the catechol. This catechol again oxidize to different pathway. Let's suppose can OH OH OH. It can break over here. It can break over here. Let's suppose it break in between the two oxygen OH molecule group. So the product will be COOH COOH, and if it is break over here, it forms COOH OH, and this is the form. Now another now coming to the monooxygenase, we all know about the cytochrome P450 monooxygenase. Monooxygenase is the cytochrome P450. P450 means it absorbs the light around 450 nanometer region. That's why its name is P450. So it can transfer RH in presence of oxygen plus 2 electron plus H plus 2 ROH. Camphor to have 5XO camphor 5 hydroxycamphor. As previous class we discussed about that. Now question is that this is iron cytochrome P450. Its structure also iron heme unit. It has the heme unit with the axial different axial ligand than the catalase and peroxidase. Here the sorry, cysteine is present. Okay, and this is the weakly bound OH molecule. It also undergoes in presence of Further undergo it forms the Fe4 oxospecies and the ring cation dot radical bar 1 system. Okay, this also form the same as well in the peroxidase and the catalase, but only here question is that cytochrome P450 transfer oxo to the substrate, but catalase and the peroxidase transfer electron to the substrate only. Okay, now why this is happening? Now here the coming the protein chain, protein environment that is present around this all those enzymes, they are playing a crucial role for a particular reaction. Let's suppose the cytochrome P450, here the iron 4 oxospecies with the positive radical porphyrin system. Here the cavity, the protein cavity such that it can allow the substrate to come closer to the iron 4 oxospecies. So that here oxo can transfer to the this enzyme, the oxo group transfer to the substrate. But in case of catalase, cytochrome P450, in the catalase Fe4 and the superoxo, this here the protein chain, this protein chain, this side is block, this side is block because of the block, because of the this protein chain. Only here the dot plus, only the substrate comes from the near to the this porphyrin ring. So but here the porphyrin ring is positive anion cation radical, so it takes one electron from the substrate. So only here the anion this porphyrin positive radical can takes electron from the substrate, so only the electron transfer happening. In the same case, same thing happening at the peroxidase enzyme also. Okay, so this is the main reason why the peroxidase and the cytochrome P450 playing a defined role, although they have the same kind of intermediate. Okay, Kalpana, get your answer. So Now I'm running out of time. We'll next class we'll discuss about the oxygen carrying enzyme, the hemocyanin, erythrin, myoglobin, and hemoglobin in a detailed way. So I'm I'm stopping this meeting now. So if you have any doubts, please come on next week. We'll like to answer all your doubts. Okay, fine. Good night to all. Thank you for joining.